In section 2.6, we're going to look at the topic of related rates. When we've looked at taking derivatives on things so far, we've looked at that finding dy dx. And while it is a relationship of rates, it's a relationship as one variable changes with respect to the other, but not over time. So for example, if we take the derivative of this equation with respect to x, we get dy dx equals 2x plus 0, or 2x. So this tells us how y changes as with respect to x. Basically the slope. If we change a certain amount in the x direction, how much do we change in the y direction? Sometimes we want to compare if one variable is changing with respect to time, how fast is another variable changing? So for example, let's suppose we have a circle, and this circle is growing. Over time, the radius is getting bigger and bigger and bigger. Or we might think about it as like a balloon. We're blowing up a balloon, and the balloon is getting larger and larger and larger and larger. And we're wanting to know, as the volume is increasing, how fast is the radius increasing? So if we compare the two variables, volume and radius, the volume of a sphere is 4/3 pi r cubed. And when we take the derivative, we can take the derivative with respect to whatever variable we want, depending on what rate we're looking for. If we're looking how volume is changing with respect to radius, then we would want to take the derivative with respect to r. But if we're wanting to see how fast volume is changing over time, we would want to take the derivative with respect to time. So if we take the derivative of the left side, the derivative of volume with respect to time is dv dt. On the right side, 4/3 pi is a constant, the coefficient, so we leave it alone. And if we take the derivative of r cubed with respect to time, notice our variables don't match, so we have to do the chain rule. The derivative of r cubed is 3r to the 1 less power, and then we have to take the derivative of our base, our inside function. So the derivative of r with respect to t is dr dt. So we can come in, our 3's cancel. So dv dt equals 4 pi r squared times dr dt. So if we know how fast the volume is changing, we can find out how fast the radius is changing. Or if we know how fast the radius is changing, we can find out how fast the volume is changing. So let's suppose that air is being added to the balloon at 12 cubic inches. Let's find out how fast the radius is changing. Find the rate at which the radius is changing when the radius is 4. So find dr dt. This stands for the rate at which the radius is changing over time. This 12 cubic inches per second, that's a change in volume. If we are adding this volume to our balloon, our volume is changing, and this tells us how fast it's changing. It's changing 12 cubic inches every second. That's dv dt. So we can substitute in dv dt is 12 cubic inches per second. 4 pi r squared. At the moment we're looking for, r is 4 inches. So when the radius of our balloon is 4 inches, we can find out how fast that radius is growing. And I don't know why I put inches there. In place of r, that would be 4, and that gets squared. So on the right side, we have 4 squared, that's 16 times 4, so 64 pi, that's dr dt. So to get dr dt, divide both sides by 64 over pi. So those cancel. So dr dt is whatever we get when we do 12 divided by 64 pi. So about 0.06. That's the radius. Our distance is in inches. Our time is in seconds. So 0.06 inches per second. So it's not growing very quickly at 4 inches. Now, let's compare that to a different or instance when the radius is 1 inch. So if we compare it to when the radius is 1 inch, our dt, that's constant. We're constantly adding air at 12 cubic inches per second. This time our radius is 1, and we want to find out how fast is our radius changing then. So on the right side, 1 squared is 1 times 4 pi is 4 pi. So if we divide both sides by 4 pi, the 4 pi's cancel. So dr over dt equals, let's see, 12 divided by 4, that reduces to 3 over pi. So about 0.95 inches per second. So when the balloon is small, the radius is growing fairly quickly, almost an inch per second. But as it gets bigger, notice the rate at which it's increasing is significantly slower, less than 1/10 of an inch per second. So think about that. When the balloon is small, if we change the radius, let's imagine that we're changing the radius instead of the volume. If we change the radius a little bit, then the added area, or if it were a volume, is a pretty decent amount. But the larger it gets, even if I change the radius the same amount, I'm changing the area a good bit bigger, a good bit more. This ring, notice this ring is significantly larger than the inside ring. So if my radius were growing at a constant rate, the larger it gets, the more my volume is increasing. But normally what happens when you're airing something up is your volume is changing at a constant rate. So in order for our volume to change the same amount as this, our radius would only be changing just a little bit. So if we wanted, I can't get the game center. If we wanted to increase our radius so that our volume is changing the same amount, we're not going to be changing our radius very much at all. So our rate at which the radius is changing, that's going to be a pretty small value. Let's look at another example. So at a sand and gravel plant, sand is falling off a conveyor and onto a conical pile at a rate of 10 cubic feet per minute. So we have the cone. And we got this conveyor. and sand is falling off the conveyor onto this pile, and the pile is going to be growing. And it's going to maintain the same conical shape. It's just going to be getting bigger and bigger and bigger. And they tell us that the rate in which sand is being added to it, so that's how fast the volume is changing, is 10 cubic feet per minute. It says the diameter of the base of the cone, so the distance all the way across of the base of the cone, is approximately 3 times the altitude. So the altitude is how tall the cone is. So we could call that the height. At what rate is the height of the pile changing when the pile is 15 feet high? Or you say, how fast is h changing when the height is 15 feet? So if we're looking for how fast h is changing, what we're looking for is dh dt. Now they give us the volume of a cone is volume equals 1/3 pi r squared times h. Now notice this formula is dependent upon the radius and the height, and that'll give us the volume. We're given one rate, we're given how fast the volume is changing, and we're wanting to find how fast the height is changing. So if we can get to where we only have one variable on the right side related to volume, then we can relate those rates together. So we want to get rid of the radius. And this is how we're going to do it. So this is known as our primary equation because that is our main formula that relates our variables. This is a secondary equation. We're going to use it to eliminate one of our parameters. So d for 3h, remember that diameter is twice the radius. If we divide by 2, the radius is 3h over 2, or 3/2 the height. So we can replace r in our formula. V equals 1/3 pi times 3r is 3h over 2, that squared, and then times h. So volume, volume is 1/3 times pi. If we square this, we square the numerator, 9h squared, and we square the denominator. 3 goes into 3 once, 3 goes into 9 3 times. H squared times h to the first is h cubed. So on top we have a pi, we have a 3. On bottom we have a 4. And that's times h cubed. So that's a formula that relates the height to the volume. If you tell me how tall it is, I can tell you what the volume is. So now that we have an equation that relates volume to height, we can relate their rates of change. If we take the derivative with respect to time, the derivative of volume with respect to time is dv dt. On the other side, 3 pi over 4 is a constant. That's our coefficient. And the derivative of h cubed with respect to time, notice our variables don't match, so we have to do the chain rule. The derivative of something to a power is bring down the power, do our base to the one less power, and then we have to multiply it times the derivative of the base. The derivative of h with respect to t is dh dt. So simplify that, dv dt, 3 times pi times 3, 3 times 3 is 9, times pi over 4, that's h squared times dh dt. So we're given dv dt, we're looking for dh dt. Let's solve our formula for dh dt. Last time we just plugged in values and solved for each different value, but this time let's isolate what we're trying to find. So if we want to get the coefficient to the other side, we would multiply by 4 and divide by 9 pi on both sides. So those cancel and those cancel. To get rid of h squared, we would divide both sides by h squared. So the h squareds cancel, so dh dt, we could write this several ways. We could call this 4 dv dt over 9 pi times h squared. So we're given dv dt, and that is 10 cubic feet per minute. And we're wanting to find out how fast is the height changing when our pile is 15 feet high. So if we plug in 10 for dv dt, and for h we plug in 15 and then square it, that'll give us dh dt. So we have 40 on top, on bottom we have 15 squared times 9, 2025 times pi. So 40 divided by 2025 times pi, 0.006, about 0.006, and that's height, which is in feet, over time, which is in minutes. If we wanted to convert that to inches, we could do that. If we've got feet on top, we would want to put feet on bottom, inches on top. 1 foot is 12 inches. So 0.06 times 12, 0.07, so 0.07 inches per minute. If we wanted to convert it to inches per second, we can convert minutes into seconds. In 1 minute, there are 60 seconds. So if we divide by 60, 1,000th of an inch every second. So just depending on how we want our answer. We could just leave it like we had it to begin with, as feet per minute. So by the time the pile is 15 feet tall, it's not getting taller very quickly. If we look at our formula that relates our rates, our h and our v, if dv dt is constant, if we're increasing our pile at a constant growth volume, adding the same volume every minute, as h gets bigger, we're dividing by a bigger and bigger and bigger number. The bigger number we divide by, the smaller this gets. So when our height is, let's say 1, we're growing at 1 rate, but as our height gets taller, then the rate at which the height is changing is slowing down. By the time h is 10, 15, 20, we're dividing by a significantly larger number. Think about if h is 20, 20 squared is 400, we're dividing all that by 400 times 9 pi. So the rate at which the height is changing is getting pretty slow. When our cone is small, if we add some mass to it, add a volume to it, it's going to grow a pretty good bit. But when it gets pretty tall, if I add the same volume, let's say from there, if I add the same volume, then that's got to cover a lot of area. So my height isn't going to change very much as it grows. And all of these problems of related rates, we're relating two different rates. So we need to write an equation that relates our two different variables, whether it be volume related to radius, or area related to height, or area related to the width. We need some formula that relates our two different variables. Sometimes that takes more than one equation to do. Sometimes we might have an equation, for example, the area of a rectangle is length times the width. But if our rectangle is going to be a similar rectangle, notice we have two different variables here. We might only want one variable there on the right side. So we would need an equation that relates length and width. We might be told that for our given rectangle, the length is always 3 times the width. So we could replace length with 3w. So this would give us an equation that relates area to width. Or if we wanted area related to length, we could get rid of w. So if we solve for w, w is L over 3. So instead of replacing L, we can replace w with L over 3. So area is 1/3 L squared. Once we have an equation that relates the two variables that we're changing, then we can see how their rates are related. Take the derivative of both sides with respect to time, and this will tell us how area is changing over time compared to how the length is changing compared to time. So we have two rates, and we can compare them. If the length is changing at a certain speed, how fast is the area changing? Or if we know the area is changing at a certain speed, how fast is the length changing? All of these pretty much are going to require, quote unquote, the chain rule, because our variable that we're taking the derivative with respect to is going to be time, and none of those variables are going to be time. So we have to use our chain rule, our general power rule, things like that.